Hey everyone, welcome back. Over the last several videos, we've learned a lot of new stuff about working with line integrals and several different options for how to set up line integrals, different contexts that they're used in. So I wanted to kind of take a moment and step back and work through one of these examples that highlights just each of the different ones that we've talked about in recent times and when it's appropriate to use which setup. So for this particular example, we are going to set up all of these that you see here as the standard integrals using whatever appropriate formula for each one. And we will assume the same curve for all of them. We'll have a helix that is parameterized by r of t equal to cosine 3t, sine 3t, and 2t, where t is between 2 pi and 10 pi. And we will have each one of these 4 examples here, with the first being working with a vector field, and then the last 3 being a little bit more similar to the very first setup for line integrals that we did earlier. If you are taking notes on this, my recommendation to you would be to leave a few lines between each one of these right here, because what I'm going to do before we jump in and work all of these examples is I'm going to highlight the key features and explain why we're going to use what strategy with each one. So I'll add some notes here before we actually get started computing anything. So, all right, that being said, well, let's go ahead and start breaking down what each one of these look like. Okay, so this first example that we have right here, we are given a vector field, which means they should actually have a little arrow over the top of that one. So since we have a vector field, we wind up using this format right here. We have this dot product between f and then the change in the curve that is occurring. So with this vector field, there's 2 options for this. It can be either a conservative vector field or a non-conservative vector field. And so the very first thing you should do when you start working with these kinds of problems is check to see if it's conservative. If it does wind up being conservative, we are going to use that the fundamental theorem for line integrals, which says that if you take the potential function that it came from and evaluate it at the endpoints of your curve, then you wind up getting the value of that whole integral, and it saves you quite a bit of work. However, if it is not conservative, I guess this is going to be a little bit tight here. I should have left more space. We're going to use the formula integral from a to b of our vector field evaluated at the parameterization of our curve. And I'm running out of space. Dotted with r prime of t dt. Okay, so that's what you use in case you were working with a vector field and you're looking at this format right here. It either needs to be conservative or not conservative, and then depending on which one it is, you can choose an appropriate formula for that. Now, these next 3 that we're looking at here, though, are going to be more like just kind of like the standard line integrals. So these are standard line integrals. They have no dot product in them. Okay, so that's kind of the big thing to note, is that there is no dot product. Everything that you're working with in this is that winds up being in the resulting formula is strictly a number. Your function here is just after you've plugged everything in, it's a number, not a vector like this right here. And what you get in the resulting formulas for evaluating these are also numbers. So let's take a look at these a little bit more closely. So when we work with this kind right here that's got a dy, this is telling us that we only care about the y direction of the curve. Which means that we want to use the integral from a to b of little f evaluated at r of t times the derivative of the parameterization, the y component of the parameterization. just like so. So these are both numbers. There's no dot product or anything like that. But that's really pretty much all there is to that, because we really only want to consider the y component. Okay, for our next one, it looks very, very similar. We're integrating over a curve C, f dz, except now we only care about our z direction. So we're going to use a very similar formula to what we did up here. It's going to be the integral from a to b of little f evaluated at r of t. But this time, instead of time being multiplied by the derivative for the y component of our parameterization, it's going to be times the z component of the parameterization. It's like so. And then finally, for our last one here, ds is meaning that we're going to care about the entire curve, the length of the whole curve, and what's happening on that whole, just really what's happening on the whole curve there. So we want to use the integral from a to b of f evaluated at r of t times the length of r prime of t. And the reason that we take the length here is because this is the whole vector. So it's got the y component, z component, all of that stuff thrown in there. And we need to use a number for these integral, for this kind of integral. Okay. So anyway, that's kind of the main idea, kind of distinguishing each of these that we've looked at so far. This one, when you're working with a vector field, everything is a vector. So there's that nice dot product in there. And then for the other kind of more standard line integrals that we've been looking at originally, you just have to keep in mind when we only want to look at y component versus the x component versus the z component versus the whole curve. And you can tell that by looking at what's at the end of the integral there. Okay, let's go through and actually work these out. We're going to use these ideas that we've talked about here. So for part A, we were told that we're finding the integral over c of f dot dr, where f is the vector field x, z, y squared x, and z cubed y. So the very first thing we're going to do is check to see that it's conservative. And since f is a three-dimensional vector field, we're looking at taking the curl, which is the cross product between this kind of gradient type operator and the vector field itself. And we want to make sure that that is equal to 0. So let's take a look. So we end up with d dx, dy, dz, and then my components from f, xz, y squared, x, z cubed, y. And this is equal to, we have I hat times partial with respect to y of z cubed y minus the partial with respect to z of y squared x. Okay, so before I go any further, one thing that I like to do when I'm working with these, like determining whether or not it's conservative, I need every single component of this resulting cross product to be equal to 0. And so, I mean, like, I can look at this right now and say, okay, this piece right here, because there's no z in that, that little piece there is equal to 0. But if I look at this right here, there is a y there, and I'm going to get z cubed. And that's not always going to be 0 for any value z. I mean, like if z is equal to 1, then we don't get a 0. So I already know that my resulting vector isn't going to be equal to 0. So I'm not even going to bother to compute the other two. So the I hat component is not equal to 0. So our whole thing cannot be equal to 0, which means that we already know that it's not conservative. So a lot of times you don't even have to make it very far into that test to check to make sure. Since it is not conservative, we are going to use that whole equation, integral over c of f dot dr equal to the integral from a to b of f of r of t dotted with r prime of t dt. Okay, so in order to do that, we're going to need a parameterization for the curve, and actually it's already been given to us. So we know that r of t is equal to cosine of 3t, sine of 3t, and then 2t. And that t is between 2 pi and 10 pi. So I know that my derivative is equal to, let's see here, I'm going to get negative 3 sine of 3t, and then 3 cosine of 3t, and then this is just going to be a 2. So, well, this guy right here, this is my x component, this is my y component, and this is my z component. And so I just got to plug each of these into this guy right here. And let's see if I have enough space here. Okay, so I'm going to have x times z. So it's going to be 2t cosine of 3t. And then y squared x, so sine squared 3t times cosine of 3t. And then finally z cubed, which is going to be 8t cubed times y. So sine of 3t. Oh, it did fit. Okay, great. So now all I got to do is plug these two pieces here into my integral here. And yeah, that'll be pretty much it. So our integral over c of f dot dr is going to be equal to the integral from 2 pi to 10 pi of, well, this whole thing right here. So I guess I already know that this isn't going to fit too great. Cosine of 3t sine squared 3t cosine of 3t, and then 8t cubed sine of, oh no, 3t. Whoop, okay, that's the end of that. And then we are dotting that with r prime of t. That's going to be the negative 3 sine of 3t, 3 cosine of 3t, and then 2 dt. Okay. Well, now we get to take that dot product, which I guess I'll move this equal sign over here, and maybe we have a chance of fitting it all in the same line. So I just got to match my components up. So I've got 2t times, or cosine 3t times negative sine 3t. So I'm going to get negative 6t cosine of 3t times sine of 3t. And then plus sine squared 3t times, oops, looks like it'll get 3 sine squared 3t times cosine squared 3t. And I guess I do actually need a new line, plus 16t cubed sine of 3t dt. Okay, so now this is kind of the point in your homework where you go back and look at the original instructions and check to see if you were asked to evaluate that. And we go back and we look at our original instructions and see that we were only told to express the following as standard integrals. Okay, so we're not going to compute this. We're just going to leave it just like that. This is actually, I mean, it's definitely doable to take an integral of like this right here. You could totally do that by hand, but it would be quite tedious. So not necessarily the best, I don't know, not the most fun, but you can leave it just like that because the instructions say so. Okay, but anyway, this is how you work with vector fields. Again, the idea is that you have that dot product because everything is a vector. So yeah, let's look at our more standard line integrals then. So we have our example B, which was the integral over a curve C of f dy, where little f was equal to e raised to the x cubed y squared z. Okay. Now, since we are looking at the dy here, we're doing the integral from a to b of f of r of t times y prime of t dt. Okay. Now, our curve, once again, was already parameterized for us. It's r of t equal to cosine of 3t, sine of 3t, and then 2t. And then t is between 2 pi and 10 pi. Okay. And now I guess I just need my derivative. So r prime of t was equal to, we had said, -3 sine of 3t, 3 cosine of 3t, and then 2. Okay. So I mean, like, a lot of the work's already really been done for us, so we're just going to recycle some of this information. Okay, so to fill in this right here, well, I'm just going to go ahead and label these. This is my x prime of t, this is my y prime of t, and this is my z prime of t. Okay, so I have my y prime that I need right there, and f of r of t is really just going to be equal to e raised to the cosine cubed of 3t times sine squared of 3t, and then 2t, like so. So now really all we got to do is just plug everything into this right here. That's going to be the equal to the integral from 2 pi up to 10 pi of e to the cosine cubed 3t sine squared 3t, and then 2t, and then times 3 cosine of 3t. This is from y prime. And then dt. So yeah, that's all you got to do there. Once again, we're told to just set up the integral. We're not told to evaluate it. So, I mean, I don't know how you would evaluate that anyway. So yeah, just leave it just like that, and you are good to go. So let's do part C, which I think asks for basically the same thing, except now we're looking at dz. Okay, and we still have the same function, everything, which is nice because once again we get to use or reuse more information. So since we're looking at dz now, it's going to be this exact same formula that we had earlier, except now we have z prime instead of y prime. Okay, and we actually already found z prime. It's equal to 2. Actually, I think we're already ready to go ahead and plug everything in. We have the integral from 2 pi up to 10 pi. Because all this information here, this is the exact same setup as what we had up here. Same function and everything. So 2 pi to 10 pi from earlier, and then e raised to the cosine cubed 3t sine squared 3t, and then 2t. And then I guess I have a 2 from the z prime. I'm just going to put that here in front. dt. Once again, no clue how to integrate this thing. It's one of those things, you just throw it into a computer and it'll do the thing for you. Maybe. And but we're not told to integrate it. We're just told to set it up. So that's all we're going to do with that one. Okay, part D, integral over the curve f ds. So, and then f is our same function, x, y, z, equal to e to the x cubed y squared z. And this time we care about this whole, the whole change in the curve, both ups and downs and side to side and all that stuff. So this is equal to the integral from a to b of still f of r of t. So we still get to reuse this piece of information here, but now we want to take into account the overall change. So we take the length of the whole derivative there. And I guess we probably still need to recompute that part. So I guess I'll do that off to the side here. Length of r prime of t is equal to the square root of 9 sine of 3t, and then plus 9 cosine of 3t, plus 4, I think. Yep, 4. And this is just going to simplify down to root 9 plus 4 here because the sine, those should be squared. Sine squared, cosine squared right there. So that's just equal to root 13. So we still have the same bounds of integration, integral from 2 pi up to 10 pi. F of r of t was e to the cosine squared cubed 3t sine squared 3t and then 2t. And then I just have to multiply by my length of my derivative, which was root 13. And since that's just a number, I'll put it in front, dt. So yeah, that's pretty much it. That's all there is to that problem. I mean, I know they look really similar and we wind up reusing a lot of the same information over and over again, which is really nice. But the main thing is just remembering that you do have those different basic setups here with depending on whether or not you have that dot product due to the vectors. So then you might be able to use the fundamental theorem of line integrals, or you may have to use a different expression to get that dot product, or you may just simply be looking at that line integral expression that we looked at earlier. So yeah. So yeah, that's comparing the different integral setups and kind of summarizing everything that we've done. I'll see you guys next time.